Okay, here we go again. Welcome again this morning. I hope you can hear me. If you can, please give me a thumbs up so I know that the sound is coming through. Excellent. Thank you very much. So this is the last, as I'm sure you know, this is the last lecture before tomorrow's midterm. So maybe just a little bit more information about the midterm, even though, of course, there's we should get going with linear momentum then again. So the midterm tomorrow will have a Zoom link that will be posted in the exam header. You'll be able to see the exam header on UMLearn later today. We just write the exam in one section and then copy it over. So we have to make sure that everything's finalized before we can copy it over. Again, the exam is 10 multiple choice questions. They're problems. I think the majority of exam questions are problems. There may be some conceptual multiple choice questions in there as well. But the problems are, essentially like what we do in class or what you prepare for the assignments, with the only difference that you'll have to pick one of 5 answers. The correct answer may not be listed, but there will be, the instructions are to pick the answer that's closest to the correct answer. Normally, though, you should expect to see the answer listed, or at least something that is that's close enough. There will be invigilation through Zoom, so everyone will have to have Zoom on, and will have to have their camera on. Okay, that's probably all I still wanted to say about the midterm. I do want to reassure you that that it's not going to be terrible. This is just a physics exam like any other, and the midterm is indeed tomorrow for those of you who didn't know. So there are going to be maybe some theory questions, depending on what you call theory. Obviously, I'm not going to ask you to give the formula for for kinetic energy, because it's an open book exam after all. So you could just look it up, and that's kind of pointless. But there may be questions that are probably, from your point of view, you might think of them as theory. For example, deriving an expression and then picking the expression among the answers that is the correct one. So you can use tablets, you can use your computer, you can use all of the resources in the course that are legitimate resources for the course. So don't think that I'm giving you somehow the freedom to use Chegg, because that's of course not allowed. You will have to scan in your work and submit it after the fact. That will not be graded. That's just for reference for us. And you can write that work that you've done to get to the answers. You can write that on whatever paper you feel comfortable in. Okay, so let's get started with some of the material for today, because we don't want to get too far behind either. The topic where we left off was linear momentum. So we introduced linear momentum and we introduced impulse. And so if we go back to the whiteboard here, so linear momentum we introduced as linear momentum is mass times velocity. So this is a vector quantity. It has a direction and a magnitude. That's what that means, right? We introduced impulse, which is the change, or which is the force times the duration over which the force applies, an average force times the duration over which that average force would apply. Or of course, if we want to write this more accurate, it's an integral of the force as a function of time over dt. And that is going to be equal to the change in momentum. So the first part here is definition. The last part is what does it cause. The impulse or the force causes a change in momentum. So one of the things in physics that we often like to say is that in mathematics, the left-hand side is equal to the right-hand side in these expressions. In physics, there's somewhat more of a directionality to this, right? There's something that is the cause, and there's something that is the effect. And maybe it's not always clear what is the cause and what is the effect. But there is, this equal sign is in some sense not entirely symmetric. So let's now imagine that we have multiple particles. Let's say we have two particles that are interacting with each other. The one particle is pushing against another particle, or one mass is pushing against another mass, and they might have different sizes. So there's going to be a force from mass 2, a contact force in this case, a force from mass 2 on mass 1, we'll call this F2 on 1. And there will be, by Newton's third law, there will be an equal and opposite force that is pointing in obviously the opposite direction with the same magnitude, that is F1 on 2. That's the force of mass 1 on mass 2. So this is expressed as F21 is minus F12, and that is Newton's third law, right? You should all know Newton's third law by now, especially if you don't know it, you still have a little bit over a day to figure out what Newton's third law is for the midterm tomorrow. So in this case, F is a contact force, but of course this could be any other kind of force. We could even think of this as, if this is the Earth and some mass is falling here under the influence of the weight, we talked about the fact that there's an equal and opposite force on the center of the Earth that applies, and that has the same magnitude but the opposite direction as the weight. And so technically, when you drop something to the floor, you also cause the Earth to experience a force upward towards the object that you just dropped. So back to the forces here. F12, the force from mass 1 on mass 2 will cause a change in the momentum of mass 2. So this will cause a change in the momentum. So dp2 dt will be equal to F12. So this came from this expression for impulse written in terms of infinitesimal quantities. So that says that the force is dp dt, or F dt is dp. That's the one that's more closely related to our expression with impulse there. So F1 is the force from object 1 on object 2 is causing a change in momentum for object 2. So that's going to be m2 times dp, sorry, not p, dv2 dt. So it's going to cause a change in the velocity for object 2 as well. So we can write a very similar expression for F21, except now this will be the force that applies on mass 1. So that will change the momentum for particle 1. And that will be then mass 1 times dv1 dt. Right? So we have F12 in terms of velocity, we have, and in terms of momentum, we have F21 in terms of momentum and velocity, and we know that both of them are equal and opposite because they're forces that are Newton third law pairs. So what can we conclude from that? Well, if this F12 is equal to minus F21, and minus F21 is minus dp1 dt, and f12 is dp2 dt. That means that dp2 dt will be equal to minus dp1 dt. Or in other words, the derivative to the time of p1 plus p2 is equal to 0. And that is going to be an important expression, because we'll introduce total linear momentum as essentially just the sum over all momenta for a system that contains many objects. So in this case, this indicates for our system of two masses that the total momentum has a time derivative that is equal to 0, or that the total momentum is constant. So let's look back at what we did here. So we started from the fact that we have two masses where the only forces that are applying are the forces between them. There's no external forces here. The only forces that apply are the forces between them. That means that these two forces that apply, one on the other, one from mass 1 on mass 2 and one from mass 2 on mass 1, have to be equal and opposite. That in turn means that their momenta will have to change in such a way that the total momentum, the sum of the momenta for both mass 1 and mass 2, will have to remain constant. So this is the law of conservation of linear momentum. So conservation of linear momentum, which says that the force, the total momentum is constant. Under two conditions. And the two conditions are that there are only internal forces, there are no external forces. And there are no exchanges of mass with the outside world. So an important aspect of this is going to be identifying when those conditions are, of course, satisfied, or for which combination of objects this is satisfied. So let's look at an example. So this is something I wanted to go over before. So let's look at, for example, these two interacting billiard balls. So this billiard ball is rolling on the horizontal sheet in this direction, and there's another billiard ball that is rolling in this direction. At some point they interact with each other, so there's going to be contact forces between them. There's not going to be any external forces applying to the system. There's no mass exchange with the outside world. The system that consists of the two billiard balls and their interaction is a closed system. I should have added that here. This is called a closed system. So a closed system is a system that satisfies this, where there's no external forces. Essentially, it means that this system, this collection of interacting masses is separate from the outside world, and there's no exchange of mass with the external world. So whatever mass goes in remains constant. So that's a closed system. These two billiard balls are a closed system. When they interact, after their interaction, they'll each have changed their velocity vector, but the total momentum will have to remain constant. So in this case, if we have billiard ball 1 has a momentum in this direction and 2 in this direction in the initial state, the total momentum is the sum of those two vectors. After the collision, billiard ball 1 is now moving in this direction, billiard ball 2 is moving in this direction. The sum of those two momenta will have to be the same because the momentum, the total momentum, P1 plus P2 has to be constant. So in this case, it's the system that we're considering is the combination of the two billiard balls, because that's the system on which there are no external forces operating. Now you might ask, or you might correctly say, well, there are external forces. There's a normal force from the billiard ball table that is working perpendicular to the plane here. There's the weight on the billiard balls that is also working perpendicular to the plane. The crucial word here is perpendicular to the plane. If it's working perpendicular to the plane, it is not changing the momenta in the horizontal plane. So that's why we can treat that as an external force. That's why we can ignore that external force, because it's not applying to our two-dimensional system in the plane. So another example might be two cars, where one car rear ends the second car, so mass 1 hits mass 2, and mass 2 moves forward under influence of the interaction. Again, the system is going to be the two cars combined, and the total momentum in the initial state and the total momentum in the final state will be the same. If the first car hits the second car, if the second car speeds up because of that, the first car will have to slow down so that the total momentum is conserved. And here the system of interest again has some additional forces in the vertical direction, but we are able to ignore those because we're considering the system to be in the horizontal plane only. So this will of course allow us to calculate some interactions. In particular, we're going to be using this conservation of momentum, which is always valid for closed systems. We're going to be able to use that to calculate the final momentum and therefore the final velocity of some interactions. So one thing to remember is conservation of momentum is always valid for closed systems. We're going to look at something else later in this lecture, or maybe if we don't get to it, only on Friday, which is not valid for all interactions, but which is valid for some interactions. So we won't be able to use that. But conservation of momentum is valid for all. So this is always valid for closed systems. So the way we're going to use this to solve problems is in a couple of steps. First, we of course have to identify that the conditions for this conservation of momentum are satisfied. Are we in a closed system? Is the total mass constant, and are there no external forces? No net external forces. So that's another way to think about it. The net external forces are zero on both of these systems. If we look at the normal force from the road and the weight, the net force is going to be zero, or in other words, there's not going to be any change in momentum in the vertical direction. So we identified a closed system. We write the momentum before the interaction. We're going to introduce explosions and collisions later, but that's what we're going to call this event when something hits something else. We'll write down an expression for the total momentum after the interaction, and of course both of them are going to have to be equal, and so we can solve for the quantity that we are trying to find. So let's look at an example of two interacting objects. So let's say we have one object that is moving in this direction, another object that is moving in this direction with V1 initial v2 initial, and this is mass 1, mass 2. And what happens is both of those objects, they're covered in Velcro, and so we end up with both of them stuck together, moving with one common final velocity. So this is what we would call, I guess, this is what we don't. This is not a physics term, but I'm gonna call this a perfectly sticky collision. So in this collision, both objects stick together and start moving with a single velocity vector. So mass 1, mass 2 are both going with a velocity vector vf. So we identify our system here. This is going to be our system. There's no external forces operating on this system, and there's no exchange of mass with your outside world. So conservation of momentum will be satisfied. Okay, great. We'll write down the momentum, the total momentum before the interaction, m1 v1 initial plus m2 v2 initial, and that's p total initial. We'll write down the total momentum after the interaction. So now this is m1 times v final plus m2 times v final, or m1 plus m2 times v final. That is our p total in the final state. So now both of those have to be equal. So that means if we want to calculate, for example, what vf is in terms of the given initial velocities, we can calculate that vf is this term here. We'll divide this term by m1 plus m2, so that's 1 over m1 plus m2 times m1 v1 initial plus m2 v2 initial. So for this sticky collision, we have an expression for the final velocity based on the initial velocities. Now we wouldn't have been able to write the final velocity as a single number if we didn't have this additional condition that this is a sticky collision. If both of the particles were moving at different velocities afterwards, at v1 final and v2 final, then of course we would not have been able to solve this because we would have lacked one piece of information. So that's what we're going to look at later when we add an additional condition. However, if they're sticking together, we get an expression, and then we can analyze this expression, right? We can again take limits as we are often doing. What happens if mass 1 is much larger than mass 2? Then this here becomes mass 1, and in this case mass 2 is kind of small, so we can ignore it. So v final will be approximately equal to v1 initial. And that makes sense. If mass 1 is very heavy and mass 2 is very light, think of this as a bowling ball and a ping pong ball that are each covered in Velcro. So if they're moving at these initial velocities, the final velocity will be much more determined by the initial velocity of the bowling ball rather than the ping pong ball. And of course, the other way around, if m1 is much less than m2, then the final velocity will be approximately equal to the initial velocity for mass 2. So it's always going to be closer to the initial velocity of the heaviest object. So we can look at another situation, which is a bouncing ball that is dropped from a certain height. So we have 3 times that we look at here. We have the initial time when the ball is dropped and when it has a 0 momentum. what happens is that the momentum will increase as the ball falls under the influence of gravity. And so at some point at time t1, the momentum will be a value negative in this direction, negative p1. And that's the moment right before the ball hits the floor. So at that time, the interaction with the Earth, with the floor, has not started yet. Then there's some interaction that happens. After the interaction, the ball is now moving upwards. And for this particular bouncing ball, we're going to assume that that it reaches the same height here, and that will mean that the initial momentum that we have before we bounce back up has to be the same in magnitude as the momentum with which the ball hit the ground. The reason for that is that the kinetic energy at time t2 will have to be identical to the kinetic energy at time t1. So that means that the velocities will have to be the same in magnitude, and if the direction is only in the only changed the sense of the direction, then that means this will be p2 will be equal to minus p1 in magnitude. So t2 is right after the interaction, and then t3 is when the ball has reached its maximum height, which is the same as the original height again. So we could ask now, which systems are relevant here? So we'll have a total momentum here, you might say, that is changing. So momentum here starts at 0, and at time t1, the total momentum is minus p1. So what gives? Why did this momentum change? Does this not satisfy conservation of linear momentum anymore? Or are we not looking at the correct closed system here? So what are we doing wrong here that allows the momentum from time t0 to time t1 to apparently change without satisfying conservation of linear momentum? So I see several of you are pointing out, indeed, this is not a closed system. This individual ball is not a closed system. However, what is a closed system, or to find a closed system, what we would want to do is consider what is the mass that is, what is the force that is operating on this ball, and find its Newton's third law equivalent or counterpart. So there's going to be a Newton's third law counterpart to this force, the force of gravity, which is the force of gravity that is applying on the entire Earth because of the mass of the ball. So if we consider the mass of this ball and the mass of the Earth, and we consider the Earth and the ball one system, the total momentum will be unchanged. The increase in momentum that the ball gets will be counteracted by an equal and opposite increase or change in momentum from the Earth. So the Earth will actually increase its momentum in the upward direction by the same momentum vector here as the ball drops. Of course, if the Earth changes its momentum by this same magnitude, because the mass of the Earth is so much larger, that will cause just a tiny change in its velocity. So obviously that's not a noticeable effect. So then what happens when the ball bounces? So now we have a change in momentum that is from minus p1 to plus p2, and we already said the magnitude has to be the same, so the delta p will be 2 times the magnitude of p1. Again, where does that change of momentum get balanced for conservation of linear momentum? Well, the Earth will also change its momentum. The Earth will change its momentum from going up to going down with twice the magnitude of one of these momentum vectors here. And then, of course, when the ball moves up, now it's decreasing in momentum upwards. At the same time, the Earth will decrease in its momentum with which it's moving downwards. So in all of these cases, the system that we should consider is the system of the combination of the ball and the Earth. So not just the ball, but the ball and the Earth. And of course we can use this now to calculate, for example, what the change in momentum would be here. If we wanted to calculate the change in momentum at the bounce, at the interaction with the Earth, we would have to calculate what is the momentum before the interaction, and then we set that, then we consider the change to be 2 times that interaction. To get the momentum before the interaction with the ground, we would have to get the velocity. We can get the velocity because we know the height. We can get the time from the height. So if we combine all of that, we have the height will be 1/2 times g times t1 minus t0 squared. So that means that t1 minus t0 is 2 times h over g with a square root. The velocity at 1 will be minus g times t1 minus t0 in the y direction. So that will be minus, so then the momentum at p1 will be minus mg times that time, 2h over g in the y direction. So that's minus m, and we've got an additional factor of g there, so then 2gh in the y direction. So then our delta p, the change in momentum for this ball, and the opposite of the change in momentum for the Earth, is p2 minus p1, and we said that p2 had to be minus p1, so that's minus p1 minus p1 is minus 2 p1. That is going to be 2 times the mass times 2 gh with the square root in the y direction. So that is the change in momentum that that the ball experiences. Okay. And of course that's going to be the change of momentum that the Earth experiences with a negative sign. So ultimately, finally, what if we now combine, look at time t0 and t3? What is the total change in momentum from time 0 to time 3? Yep, ultimately all of the changes in momentum, so there's going to be a change in momentum for the ball from time t0 to t1, then from t1 to t2, and then from t2 through t3. But if you add up all of the changes in momentum, they're all going to add up to exactly 0, because we know that there's no change in momentum since we start at 0 and end up at 0. Okay, excellent. So then finally, let's talk about one other topic, which is just introducing what we're going to talk about much more on Friday. That's the types of collisions. So this is the thing that is going to be not uniformly, not universally valid. So the conservation of linear momentum is always true as long as we're working in a closed system. In this case, we're going to introduce some ideas about kinetic energy. So there's 3 types of collisions that we're introducing here. There's an explosion, which is when we have one part that goes to many parts. I don't need to explain what an explosion is, but we have, for example, one mass that sends out a couple of different masses. So if we have mass 0, and then we have mass 1, mass 2, mass 3, the initial state, initial momentum, is just the momentum of mass 0. The total final momentum is going to be the momentum of part of mass 1 plus the momentum of mass 2 plus the momentum of mass 3. And those, of course, will have to be equal to each other as long as we can consider all of these particles to be in a closed system. So as long as none of them hit something else and start interacting with the outside world. So that's an explosion, one too many. Then we have an elastic collision. That's when we have many particles going to, let's just call it equally many. So that's when we have, for example, one particle M1 interacting with another particle M2, and they're both moving out of that interaction again. And then we have, so this one will have an initial momentum P1 and an initial momentum P2. Let's say this one is P2 prime and P1 prime. So then P1 plus P2 will be equal to P1 prime plus P2 prime. So that's an elastic collision. And then finally, we have the inelastic collision, which is, let's just call it many to fewer. So that's when we're, for example, in the situation where we have the sticky collision. So this is an example of an inelastic collision. The sticky collision is an example of an inelastic collision because we end up with only one particle with the sum of the masses, where we started off from two particles. So now it will be important to distinguish those last two types of collisions, elastic and inelastic collisions, and we'll use the kinetic energy for that. In an elastic collision, the initial kinetic energy is equal to the final kinetic energy. Or in other words, if you think about mechanical energy, it means that all of the mechanical energy in the initial state is still found in the final state. Nothing has been dissipated. There is no loss that has occurred. For example, due to, I don't know, the friction that might be required, or the energy absorption that might be required for an inelastic collision. And of course, I'm already indicating here that an inelastic collision will then have a final kinetic energy that's less than the initial kinetic energy. And there's a special kind of inelastic collision that's a perfectly inelastic collision. That's when the final kinetic energy is as low as possible. So what's the lowest value it could be? Well, we have to be careful here. It cannot be zero, right? There's going to be a minimum kinetic energy that we end up with in the final state, because we still have to satisfy the conservation of linear momentum. So we still have to have momentum in the final state, which means we will have to have motion, which means we will have to have a velocity, so there will be some kinetic energy in the final state. But a perfectly inelastic collision makes that final state kinetic energy as low as possible. So it doesn't go to zero. Kf not zero, I guess, in general, since the final momentum is non-zero, again, in general. There's of course situations where the final momentum will be zero, because we started from a zero total initial momentum. For example, if we have two identical mass particles moving from opposite directions, then the total initial momentum is zero, and so then technically the final kinetic energy can be zero when all of this is absorbed in exactly all of this and ends up being at rest there, and created without any kinetic energy. So two things to keep separate: momentum conservation, linear momentum conservation, is always satisfied for closed systems. Kinetic energy conservation which we don't call that, but in an elastic state, kinetic energy is identical before and after the interaction. So elastic collisions will also have a constant kinetic energy, but this is only true if we know that we have an elastic collision, not if we have an inelastic collision. So that will of course be what we'll use as either an additional condition, the elastic condition, or the perfectly inelastic condition, or to calculate, for example, how much energy is lost in the collision by calculating what that change in kinetic energy is. And we'll come back to that on Friday.